Hey guys, it's Ron. So we're up to Lab 11, which is OSPF. I'm not going to get too in the weeds with it. I'm just going to go over some of the basics to kind of get you up and running. The CCNA objectives also don't cover, a ton of OSPF. There's a lot involved with OSPF, but the CCNA objectives just hit on some of the top things that you need to know about it. Personally, I haven't implemented OSPF in a large network, just tinkered around with it. I typically use EIGRP, but since this is OSPF, that's what we're going to talk about. Now, OSPF is a link state routing protocol. It is classless, scalable, uses autonomous systems, but is really characterized by its use of areas. So areas come into play, when segmenting your network. They allow you to kind of break it down so that you don't have to, that your individual routing tables don't have to be quite as large. You're not having to pass nearly as much information to get the network to converge. And so, they break them up into these areas. Now, the thing about areas is you have to have an area 0. It's like the base level area, and then every other area kind of feeds off of that area. And when I mean feeds, it has to have a connection back to area 0, whether it has an interface on that router, is connected to area 0, making it an area border router where it can kind of share information between two areas, or it has like a virtual link back to area 0. For CCNA, you only have to configure a single area OSPF implementation, so it keeps it pretty easy, pretty simple. Another couple things you need to know about it is that it's vendor or not vendor specific. Now, each vendor has done a slightly different implementation of OSPF, but you can get it to work between different vendors. Things you need to watch out for are some of your default timers, but biggest thing I've noticed is making sure you're using the same version of OSPF. And you're using the same costs on your links. Now, one vendor might use one method for calculating their costs. Another vendor might use a slightly different version. Cisco tends to do theirs pretty simple. They take 100 megabit and divide it by the actual bandwidth of the link. So in our case, it'll be 100 megabit divided by 2 megabit, or 100 megabit divided by 256 kilobit. So our fast ether connections are going to end up having a cost of 1 because they're 100 megabits. These are going to have like a cost of, well, it's 100 divided by 2, so about 50. And then whatever this calculates out to, it's like 300 something. So we'll go, through some of the basics of setting up. You'll see some of the same terms, links. You'll see neighbors, adjacencies, hellos. Those are all the same things we're used to in EIGRP, but we have a couple extra little things like router IDs. Each OSPF implementation is going to choose a router ID, and it can do it in a couple different ways. You, as an administrator, you can assign it that router ID. If you don't do that, it's going to look for its highest IP. And so, like in this case, it might use this IP because it's the highest IP out of these three. Now, in our case, we have a loopback address. And in OSPF, if there's a loopback address, it's going to use the loopback address or the highest loopback address that you've specified. But if you didn't have one of those, again, it's going to look amongst its interface, find the highest IP, and that's the one it's going to assign. I typically like the loopback method because the loopback is always up, so you don't have to worry about when this router booted this point, for some reason this link was down, so now it's going to come up with a router ID of this. And if I'm looking for a router ID of this, it can get confusing. So I like the loopbacks. Another thing that we need to talk about are LSAs. Those are your link state advertisements. So this is, when one OSPF implementation, talks to the next router, instead of advertising out its entire routing table, it sends out these link state advertisements that basically just contain information about its local interfaces and the costs associated with that. And then each router then ends up building like a tree of how it views the network, and it's going to use that tree to determine traffic through the network. So each OSPF implementation is going to build that tree. Next topic is broadcast multi-access. So in the case of like a fast ether connection, this is a broadcast kind of style connection. If there are multiple routers on a broadcast style connection, the thing it's going to do is it's going to elect a designated router. And it's going to use this designated router to kind of reduce traffic. It acts as like a hub of information flow. So there's going to be a designated router, and there's going to be a backup designated router. And you'll kind of see this when we implement it. Lastly, the algorithm it uses is just called the shortest path first algorithm, and it's going to end up using a when it sends out these LSAs, it's going to use the multicast address 224.0.0.6. So you know, it's efficient in that manner. Instead of sending out broadcasts, it sends out the multicast. So let's kind of get into the implementation. We'll configure router A the proper way, and then we'll kind of jerry-rig B and C. We'll just do kind of a quick and dirty kind of method. Enable config T. We'll do router OSPF question mark. So this is a process ID. So the process ID, unlike the autonomous system numbers that you saw in the EIGRP, these process IDs are locally significant, meaning that I can assign it any number between, you know, the 1 and 65,535, and I don't have to worry about, you know, matching that number up with the rest of my routers. Now you'll want to choose a number that you can kind of remember. I'm just going to choose 1 because it's easy. And we're going to specify our network statements. So we've got, since we're on router A, we've got network, we'll start with the 0.1 interface. We'll do 192.168.0.0. Now we're not specifying the classful IP address, kind of like we did with some of the other routing protocols. What we're actually specifying is the full network address. So then afterwards, here's where we're going to put our wildcard mask. Now, if you don't know how to do wildcard masks, go ahead and watch my wildcard video. It's pretty easy to do. You end up taking 255, 255, 255, 255, and subtracting the network mask. So in our case, since this is a /30, it ends up being a 252. So 255 minus 252 is 3. So this becomes 0.0.0.3. And here we're going to go ahead and specify our area number, right? So area 0, right? So let's go ahead and specify the next ones. So network 192.168.0.8, and this is this interface right here. Again, it's a 252, so 0.0.0.3, area 0. Network 192.168.1.2. Now this one's a little different because it's a /32. So it's a 0.0.0.0, area 0. Network 172.16.2.0. And this is 0.0.0.0. Now we have a /27, so that's a 224. So 255 minus 224 ends up being 31 in area 0. Now I'm going to add an extra interface in here. You don't see it in the picture, but I've hooked up another router to router A just so that you can see that DR and BDR. And this is network 192.168.0. It's the 12 network, 0.0.0.3, area 0. Okay? Now that should build a relationship because that router's already programmed. In the meantime, well, there it goes. Pops right in. So this one used a router ID of .13, so it does not have a loopback address. So it chose its highest interface IP. All right. Now there's a couple other little things we can do in here. So we can end up doing a passive interface FA00. So that's the best way to do it. You don't need to be sending out that information where your users are. So we'll make 00 passive. Now, just for fun, you can do a router question mark, so router ID. So if we didn't want it to choose the loopback address, we could specify in here exactly which router ID we wanted to use. But in this case, I'm fine with using loopback addresses. So we'll go ahead and we'll configure B and C. And again, we're gonna use the cheater method here. Fig T router nice router OSPF question mark. Again, we can use whatever process ID, so I'll use a process ID at 2. We'll go ahead, specify our network. Now here's where we're going to cheat. Instead of actually specifying the networks, we're going to say every network assigned to area 0. So it should build a relationship. There it goes. So it built a neighbor with 192.168.1.2, or it built an adjacency with neighbor 192.168.1.2, which is our loopback address right here. So that's good. And won't worry about doing passive on that one. I'm going to come out here, enable config T router OSPF 3. And again, I could have made that 1, 2, whatever I wanted. Network 0.0.0.0.255.255.255.255. Now, again, I don't recommend doing this in a production network, and definitely this goes against the CCNA objectives. If you're going to learn OSPF, you need to know the wildcard mask method. Again, I'm just using this for sake of time. So we went ahead and built it. So we'll go back to router A. We'll do a show IP proto, which is show IP protocols. Okay, what do we got? We got OSPF 1. Again, this is the process ID, which is only locally significant. It chose a router ID. Now that is our loopback address. These are the network statements that we ended up putting in. We set fast ether 00 as passive. We're trading information with these two routers, with B and C. A distance, or an administrative distance, of 110. Okay. Show IP OSPF neighbor. Now notice here that we have our 3 relationships: router B, router C, and then the router that's hanging off here to the side. And the one to the side, notice DR. So the router that was hooked up to router A got elected as the designated router. Okay, and that might be because, you know, I had OSPF turned on first on that one, so it elected itself as the DR, and because router A is coming in behind it, it becomes the backup, so it's the BDR. Now, if the DR fails, you know, my router should become the DR, okay? And then another election should ensue to find a replacement BDR. Okay, so let's go ahead and look at show IP OSPF interface. So what we see here is that gives us a lot of information. So this is our interface. It's up. This is the IP to it. It's assigned to area 0, which is on a broadcast type network. Okay. Process ID 1. So it's all the same information we've seen. But here now we get to see our actual timers. So this is hello timer of 10, dead timer of 40, wait timer 40, retransmit 5. So these need to match on your various links. All right. So if you modify one, again, you need to be modifying the other. Let's see here. I know it's here somewhere. Okay, so we have an adjacency on this interface with this guy, and he is the designated router. Okay, so he's the DR for that network. If we look on some of the rest of these, it doesn't talk anything about DRs and BDRs because these are point-to-point networks. And if you notice, serial 00 has a cost of $3.90, and that's 100 megabit divided by 256 kilobit. All right. If you come up here to some of our fast ether, it has a cost of 100 megabit divided by 100 megabit. So too easy. Serial 01, serial 00, cost of 50, or 01, I guess, and that's it. So we didn't see fast ether 00 because again we made it passive. And that's pretty much it for gathering information there. So let's see. So we did show IP OSPF neighbor. We just did show IP OSPF interface. Let's do a show IP route. So you see here we have O's for our OSPF announcements. Administrative distance of 110. And then the actual cost that was assigned to it. So a single hop was 51. If it has to take a double hop, 51, it ends up coming out 101. All right. So the 390 isn't in here because it says, well, that the cost to take 2 hops is less than this 1 hop, which is good. That's what we want. So now we can go back in and assign our own costs to these things. Oops. So if I did a interface FA 00, I could do a IP OSPF, little question mark, and we could assign it a cost, right? So we do cost question mark. We can assign it anything from 1 to 65,535. Okay. Another thing that we can do is a priority. Okay. So when we talked about the DR and the BDRs and all that, by default, these are going to have a priority of 1. Okay. And the link that has the highest cost or the highest priority ends up winning, right? So if I set this one up to be a higher cost and reboot or restart the OSPF process, it should become the DR. Now, if I assign it a priority of 0, that means it will never become a DR or a BDR. So we can do IP OSPF question mark, oops, priority IP OSPF priority, if I could spell. So we can assign it any number from 0 to 255. And again, 0 means it's never going to be elected. 255 is pretty much means it's going to always be elected the DR. So this is one way for you to kind of structure your network. So you know, okay, it's going to come up with this router ID because I specified it, or because I specified a loopback address. And this broadcast multi-access network, this one is always going to become the designated router because it has the highest priority. You know, so you can kind of break down your network and get it to do what you want it to do. You can go in and make your own costs. So it's all up to you how in depth you want to get. So that's pretty much it that I wanted to cover through the lab. As long as you know how to go in, add in your network statements using that wildcard mask. Need you to understand that those priorities are locally significant. On these broadcast multi-access networks, you're going to have these DR BDR elections, and those you can rig those by setting priority numbers or having the highest router ID. So those are the kinds of things that I wanted you to get out of OSPF, at least for the CCNA level stuff. Let me know if I missed anything or you didn't quite understand something. I try to respond to emails as quick as possible. So thanks again for watching the video. Again, I hope you learned something.